looks like we are recording. Okay, we are dealing with chapter 14, and this deals with atmospheric pressure and stuff like that. So what is it? Oh, it's gases. So let's go on to look at this. Okay, atmospheric pressure is the pressure that we experience due to the weight of the atmosphere that is above us. So here's us, right? If you look at the little stick figures over here, then if you look up Mount Whitney, here's Mount Everest, tallest mountain in the world. 50% of the atmosphere is below a height of 5.6 kilometers. It looks like Mount Everest goes up almost 10 kilometers, which is like 6 miles. Can you imagine? 6 miles straight up. 90% of the atmosphere is below 20 kilometers, 99% below 30 kilometers. At 40 kilometers from ground, we have the ozone layer, and this is a scale of the kind of temperatures that you see as you go further higher and higher up into the atmosphere. Minus 55 degrees centigrade up here. So the weight of all this air above us presses down on us, creating a pressure. At sea level, that pressure is 101 kilopascals, 101 kilopascals. Pascals are units of pressure, newtons per meter square. Next slide. Okay, so this is an illustration of the reality of atmospheric pressure. This was an experiment called the experiment of the Magdeburg spheres, done in 1654, where what they did is they created two metal hemispheres like this. They sealed them probably with a rubber gasket or something of that sort, and then they evacuated it, right? They sucked out all the air out of the hemispheres that were sealed together to form a sphere. Right? Then what they did is they harnessed, okay, here's the sphere, the hemisphere that's been joined, so creating a sphere that's evacuated. They harnessed teams of horses, and the idea was to use the horses to pull the spheres apart, right? So these guys huffed and puffed, and those guys huffed and puffed until the house fell down, right? And what happened is two teams of horses could not pull the evacuated hemispheres apart. So question to you guys, right? Sorry?
That was a lot of horsepower.
That's true. Two teams. I don't know how many horses there are in a team. If you look at this picture.
It's like 8. Oh no. 2, 4, 6, 8, yeah.
Okay. So, looks like, okay, good observational powers. Okay, so question. Were the hemispheres sucked together or pushed together?
I would say pushed together.
Okay, pushed together by the horses. The horses are pulling them apart
By the atmosphere.
by the atmosphere, right? Anybody who wishes to disagree? Nope? Okay, you're right. It's pushed together by the atmospheric pressure. So a lot of times we think of suction as something that we are actually sucking on something, creating a negative pressure, but really what's happening is we are creating a lower pressure zone, and we'll see this in one of the following slides, right? Okay, oh there. We won't see it yet. Oh no, I think we will. So here is a piston with a pipe to the top that's sent off to a vacuum pump that evacuates, sucks out the air, so there's no air here. Now, that's the piston head, and here's the piston, whatever this thing, the thing that slides up and down. So, and to this is attached an anvil, and what happens is the cylinder right here, this head moves up, pulling this anvil upwards. Is this object, is this pulled up, right, because of the vacuum, or is it pushed up? It is pushed up. It's not pulled up, because all that we're doing by using the vacuum pump is to evacuate this. So we got a low pressure zone. Low pressure zone by itself does nothing. It's like saying, which is not true, but it's like saying there's nothing here. Nothing cannot do something, right? How can nothing do something? It's impossible for nothing to do something. Nothing can only do nothing. But it can't even do nothing because it just can't do anything at all. Right? Yes. So it's like saying that there's nothing here, so it can't do anything. So what's happening is there's atmosphere up here, so there's an imbalance in the force. No atmospheric pressure here, high atmospheric pressure here, so it just pushes us up, which means this object is pulled up by this object, and this is pushed up. So this object is pulled up by this, but this object is pushed up by the air. Yes, mademoiselle?
I was talking to somebody the other day about clean rooms.
Mm-hmm.
So is that kind of the same
theory, like, but it's the opposite, like they put more pressure into the room so that,
You're talking about a positive pressure room
I think so, like if they don't want dust.
in a clean room in a hospital or a semiconductor fab?
It's a graphic design shop, but they, like with print machines and stuff, so
Okay,
something similar to
so if
that.
they're trying to keep dust from coming in at the lowest level of clean room, you'll have a positive air pressure. So you actually pump air into the room. You typically have HEPA filters that the air comes through, and the HEPA filters have very small holes in them, so they don't allow dust particles and so on to come through. I mean, they're graded according to size, so it might be less than a micron in size or something, that the holes, the air comes through, and then you keep a positive pressure, so air always leaks out the door. You don't have any air coming in, right? And but there are higher levels of clean rooms than that. So it's like number of particles per centimeter cube. The protocols become stricter and stricter, more stringent. Probably the most stringent protocols are in probably in infectious diseases, airborne disease labs, like National Institutes of Health and stuff like that, which is even higher protocols than what we see in any graph.
They just push more air into the room to create a higher.
So yeah, but in this particular kind of clean room that you're talking about, they have air coming in through like the vents there, but at a higher pressure.
Okay.
So there's a positive pressure, so the air is always leaving the room. You never have air coming into the room, right? Okay, so looking at the pressure over like a square or whatever that is, 2 centimeters. Let's make that an inch, right? Like a square inch has a certain amount of pressure. What's happening is there's a column of air above this all the way to the very top of the atmosphere. That air has a certain weight. So that weight is what is creating a pressure on this square inch or square centimeter down here. That's what this is illustrating. The weight in this pipe all the way to the top of air is what is creating the air pressure at the bottom there. Okay, now same kind of concept here, where guy and a girl, they're drinking out of whatever, soda pop, something of that sort, right? Straws. So as the guy sucks up the liquid through the straw, is he pulling up the liquid, or is the liquid being pushed up into his mouth? Okay, same principle, right? What is happening is all that he's doing by creating the sucking is basically creating a low pressure zone in his mouth and a low pressure zone in the straw. If his mouth were not here, what would happen is the straw would have the same pressure as the air over here. So they'd be balanced, so there'd be no flow of air or liquid from one place to another. But once he creates a low pressure zone here, this pushes down, creating a high pressure zone, pushes down on the liquid then goes up into his mouth and into her mouth. Okay, concept behind a barometer. Bar, right at the top, any device that measures atmospheric pressure is a barometer. The meter part has to do with measurement. The bar has to do with pressure, right? So pressure meter is literally what it says. So an example of a mercury, traditionally barometers were mercury barometers, and how they make them is they take a glass tube like this, evacuate it, or you could do the same thing by turning it over. Here's this end is open, that end is closed. You turn it over, fill it with mercury, so it's completely full. Then put a glass tray over the top and quickly invert this, right? And then you kind of hold this onto the wall or something so it doesn't fall over. Now what happens is the weight of the mercury pushes down, so the mercury comes down, and there's no air here, so this is a vacuum, right? So this is a low pressure zone, it's a vacuum. But out here you got air that's pushing down on the mercury here. So the air pressure pushing down on the mercury will hold up a certain height of weight of mercury. So it turns out at sea level you have 760 millimeters, so 76 centimeters worth of mercury will actually stand up in this glass tube. If you were to make a hole in this tube here, all this mercury will end up down here and on the floor, right? So what's holding it up is the fact that this vacuum, very low pressure there, high pressure here, pushing it up. And the pressure here is compensating exactly for the weight of the mercury from above that's pushing down. So this is how a mercury barometer works. Have you ever heard the the mercury is falling? Have you heard that term? Read it anywhere? In olden times, like you had the sailing ships and so forth, and one of the ways that they were able to determine if a storm was coming was they would have a barometer of sorts like this, and they look at the mercury and they would check the level of the mercury, and if the mercury was like falling, right, as they checked it periodically, you know that now you're in a low pressure zone. If you're in a low pressure zone, you know this, and the more it falls and the faster it falls, the more the severity of the storm that's coming, because the lower the low pressure zone, the more it's going to suck in all the air, right, the winds and the storm and so forth. So that's where the term a falling barometer or the mercury is falling, that kind of stuff. It's basically that the height of the mercury here is dropping as a function of time. You take measurements every 15 minutes or something like that. Okay. Now, have you ever seen this in the Phoenix area? I have not. You have? Okay. So I presume that if you go out of the cities, right, city regions, like out into the countryside and so on, you should see stuff like this. Basically what's happening is this is a hand pump, and there's basically a pipe that's going down into the water table. Now when you pump the hand pump, what you're doing is there's a piston arrangement so that as you pump, you're creating a low pressure zone, a vacuum. The vacuum then in the chamber then makes it possible for the atmospheric pressure on the water table to push as it's pushing the water down, the water then sees this low pressure zone and comes up to compensate for the low pressure here. And then there's a mechanism that gets the water out here. And so this is the mechanism by which you're getting water out. Mademoiselle?
I know that sometimes you have to prime those pumps with water. Like, why would you need to do that?
Extra credit for the question, right? And extra credit for you speaking up earlier when you did to ask another question. The reason why you have to prime the pump is because in the apps, you have to fill a certain amount of area in the cylinder there with water to create a seal so that when you're pumping it up, you're actually able to get a low pressure. Because otherwise what happens is, without priming it, there is air in the cylinder. And when you try to pull it up, what happens is the air just expands and it's not as effective as if you put the water in, right? Okay, next slide. Boyle's law. Now you've seen this in the lab, right? PV equals PV. The pressure multiplied by the volume is a constant. Boyle's law basically states that the product of pressure and volume for a certain container is a constant. So if I were to take the pressure in this room, this volume of this room, and if we were to then compress the room so that it's half the volume, right, what happens is the pressure doubles. Because same number of molecules. It's kind of like if I were to take all of you students and like squish you into half the size of the room, or take you all and put you into a telephone booth. You're going to be like stressed, right? Put you into a Volkswagen Beetle or whatever. So kind of thing. That's what's happening. So here's a tire on your car. Certain number of molecules of air, nitrogen, oxygen, all that kind of stuff, popping around, right? So that's what these things are. What happens as you increase the pressure, as you put more air in, the density goes up. You can see that there are more of these dots popping around, right? The density goes up and the pressure goes up. So as the density goes up, the pressure goes up here as you put more air into your tire. If you have a piston head, right? So here's the cylinder, here's the piston head, and what happens is you have a certain number of these molecules of gas, right? Or atoms of gas, depending on what gas it is, popping around. Now if we were to reduce the volume in half, what happens is the density goes up because all of these atoms / molecules are squished into a smaller area. So they're like kind of fighting to get out. And what happens is this increases the pressure, right? Because the pressure that we measure is really a measure of the force that's applied by the number of molecules or atoms that are hitting the sides of the structure. Introducing the concept of Archimedes' principle for air. An object in the air is buoyed up by a force equal to the weight of the displaced air. Now this is the same principle that we talked about for water. Remember we said if this room were a swimming pool and if we were at the bottom of the swimming pool, we would feel a force that's pushing us up, right? And that force was equal to our volume in water, the weight of that. So take your volume, replace it with a person who looks just like you, made completely of water, weigh that person, that weight of that person would be the force that's pushing you up from the bottom of the pool. Now we are at the bottom of this ocean of air, atmosphere. So we displace a certain volume of air. So make another person just like us, same volume, fill that person with air, 0 weight of skin, measure that person, that weight is the same as the buoyant force on us, right? So truth of the matter, I don't mean to discourage any of you, but when you stand on your bathroom scales, what's happening is your real weight is slightly higher than what you actually read on your scales.
So, what is the weight of air?
What is the weight of air?
Because if you can make the air pressure higher.
If you can, yeah, the weight goes up if you increase the pressure, right? That's something that that's something that you can probably look up at at room temperature, at sea level. What is the weight of 1 cubic centimeter of air, right?
Right, like I understand the whole, pressures, but that's, the actual weight per cubic.
Okay, if you understand pressure, then we can work backwards to the weight, right? So let's say that this is the height of the atmosphere from here to here, right? And this is a 1 centimeter square pipe, right? 1 square centimeter, like a cuboid. Now, the weight of all of this per unit area is the pressure.
Right.
So now, let's say that this is 100 centimeters. Divide this weight by 100. That's the weight of 1 centimeter cube of air.
Okay.
Right? So you're just working backwards from that number. So in principle, since we said that the atmosphere is about 40 kilometers tall, and now this won't exactly work because the weight is not uniform throughout, but let's say for a first approximation it is. Let's say that the weight goes up linearly, right? So since it's 40 kilometers tall and it's going up linearly like a triangle, we can take half, right? So take 20 kilometers. 20 kilometers worth of air applies a pressure of 101 kilopascals, newtons per square meter. So from that you can work backwards to calculate the weight, or the easier way is just Google it. I'm sure somebody's done it. What would we do before? Isn't it amazing? Like, we've become so used to the internet. It's almost like there never was a time when the internet wasn't around. There never was a time when Google wasn't around, or MapQuest, or whatever, or GPSs. Our encyclopedia, right? I know. Okay, so this figure is making the point that at ground level, a balloon is only partially inflated. So if you see these hot air balloons that are going up, they don't typically inflate them like this when they're at the ground. At the ground, at ground level, you'll notice that they're more like this, partially inflated. Then as they disanchor, or whatever the right term is, when they start floating up into the air, as they go higher and higher, then it looks like these things fill out. And one of the reasons for that, if they go high enough, is because the air pressure at the higher levels is much lower, outside air pressure. So there's less pressure pushing in. So for a given internal pressure, the balloon fills out, right? Okay, introducing plasma. We have talked about this. We said that there were 4 states of matter, right? To a first approximation. The first was solid. Heated up, it becomes a liquid. Heated up further, it becomes a gas. Heat the gas up further, it becomes a plasma. And what happens is, in a plasma, the molecules or atoms of gas are moving around so fast that they knock electrons off of each other. So now you end up with a charged gas. And that charged gas behaves differently in an electric field or a magnetic field, or an electromagnetic field. And so that is called a plasma. So you see plasmas in plasma displays, right? Or in like neon bar signs and stuff like that.
So what plasma TV is?
Yeah, a plasma TV, at least, I don't know if it still uses a plasma, but originally the idea was that you have a very small, fine emitter, a tip, where you apply a very high electrical field, and that creates a plasma that does stuff. That was the original design.
So my understanding.
It's very possible that it has morphed, drifted from that to something else. Okay, Bernoulli's principle, introducing the concept of Bernoulli's principle. Here's a person over a bridge, right? Here's a stream. The stream narrows as it goes under the bridge. Is the water flowing faster or slower under the bridge? Faster, right? So since the water, and you're right, because if a certain volume of water is coming here per unit time, per second, for all that volume to get here, it has to travel faster when it's under the bridge because the path is constricted, right? So the question, do you think the pressure is higher here or lower in the constricted region? How many of you would say higher? Show of hands. How many of you would say lower? 2. How many of you would say same pressure? How many of you'd say, I have no clue, I just want to go home and get a beer? 2. Okay. 3 maybe. Okay. I would intuitively think that because all of this is constricted, the pressure should be higher here, right? But Bernoulli comes along and says, nope, you're wrong. He says, the pressure in a fluid that's moving steadily without friction or outside energy decreases when the fluid velocity increases. In other words, if the water is traveling faster here, the pressure drops. Of course, that presumes that this particular liquid has heard of Bernoulli, right? Now, if the liquid had not heard of Bernoulli and decided it's not going to follow the principle I haven't heard of, things might be different, right? But in the absence of that, in general, the presumption is that they have. So, faster liquid means lower pressure. So, what this means is, if you have a pipe, right? Let's say that you have at home, you have whatever 1.5-inch piping that then narrows down to 1-inch piping and then down to whatever 1/2-inch pipes. Let's say. So let's say we've got 1.5-inch and then it narrows to a 1/2-inch pipe. So here's the narrow pipe, there's the wider pipe, and what happens is the water is flowing faster in the narrower pipe. The unexpected thing is the pressure here is lower according to Bernoulli's principle. So if you were sending champagne through here instead of water, let's say that you happen to be one of those multimillionaires who has champagne faucets in every room, right? So in a situation like that, what happens is let's say this is made of glass so you can look in, you'll actually see that the bubbles are smaller at this end than over here. We miss you. So is that what you observe at your home?
What?
Is that what you observe in your champagne faucets?
Yes, of course. I'm just asking about we're observing like the air in the bubbles, right?
Mm-hmm.
Well, according to what we learned a few lessons ago or whatever, the depth of the water is providing the pressure.
Okay.
So if you've got half the depth of water as over here, then that one's going to have more pressure.
Good point. Excellent point. Next question.
That's it.
Okay.
Yeah,
You're right.
I was
Extra credit.
for confirmation on that.
Extra credit to you.
Okay.
This is like along the good point. I'm glad to see you applying a previous lesson, right? Now, what happens is that the presumption here, and that's very true, there's more weight of water. If you look just at weight of water here, there's a greater weight of water above here than here. So that would cause the pressure to be greater here, which means that the bubbles should be smaller. Yes. However, that effect is a very small effect compared to the pressure change due to this change in diameter. Right? So you're right that both of these effects, in this particular case, both of these effects are pointing in the same direction. So based on what you said, if we did not take the water pressure due to height into account, you'd end up with a situation like this where all these bubbles are the same size and they're smaller, and all these bubbles are the same size and they're larger. However, taking what you said into effect, you'd expect a gradation in the size of these bubbles. The bubbles near the bottom will be smaller yet than the bubbles at the top, and the same thing here, right? But the second effect is smaller than this. So, but good point. Glad to see you're applying this. Okay. Now, you're welcome to do this experiment at home. Just watch out for paper cuts. Paper cuts are not particularly... Yes, thank you. Extra credit, right? And you definitely don't want a paper cut on your lip. But let's say you get a sheet of paper, right? 8.5 by 11 or whatever, and you hold it and you blow over the top of it. And as you blow over the top, you would expect that the paper will do what? Yes, but you'll think that I'm increasing the pressure above. So as long as you're not blowing down on the paper, let's say you're blowing down, right? That's what happens. But let's say, I have no idea if it's going to work, right? So, okay, what are you supposed to do? Maybe tear this in half. Oh yeah, that's a good idea. Okay, so if I were to do this and just checking to see if you're awake. Yeah, I see what you mean. I'll try this. Now, if you blow over the top, would you expect this to bend downwards or upwards? Okay, what it's supposed to do, right? In real life, if did it? Okay. So, what you would think, I would think intuitively when I blow, this thing should go down because there's more pressure. And in fact, that's what it'll do if I'm blowing down on it. However, if I'm blowing parallel to the top and not blowing down on it, then what happens is, right, so here he's blowing parallel to the top. The flow of air up here creates a lower pressure zone, and so the air pressure below causes it to go up, and that in part contributes to the flapping that you talked about, right? But when you actually do this experiment, sometimes it works, sometimes it doesn't work, because it's hard to blow exactly over the top parallel without blowing down on it and stuff like that, right? So this is the same principle where, you know how sometimes in places with the tornadoes and storms, you end up with a barn roof just getting lifted off, or the roof getting lifted off a house. I always thought it was because of the air pressure coming up under the eaves, right, under the edge of the roof and lifting the roof off. But according to the textbook, and it's probably right, what happens is, what is happening really is a low pressure zone here, particularly on a pointy roof. The air that's traveling over the top curves upwards over here. So see these lines of flow? The lines of flow are concentrated here, which means the air is traveling faster over here than here. So since it's traveling faster, the pressure should do what? Go up? Okay, it's traveling faster here, so pressure should go up?
Down.
Should go down, right? That's the opposite of what we think it's going to do, because of Bernoulli's principle. So the pressure is lower here compared to the pressure here inside the house. So the higher pressure in the house then pops the lid off, pops the roof off.
So we have barns that are open around it.
That's a good idea. Yeah, so you could have like a flat topped barn, I suppose, or a curved surface
You know how a lot
barn.
of them were curved.
Okay.
They're Fisher Price and they're curved.
I had a deprived
So-
childhood, so I haven't seen very many barns.
So would that make a difference? Is it just
It would make
this,
it would make a difference. Yes. Now I don't have a feeling without actually going through all the calculations to see how much of a difference it would make. Right? I'd be for a small price. I'd be happy, totally happy to do it. It'd be a fun weekend project. Okay. So now a similar experience happens with a plane, right? If you think of a plane, this is the